This is video 4 in the test 2 review, and here we're looking at a reverse problem, that is where we're giving a response y of t along with what the excitation is, in this case a unit step, and additionally what the initial conditions of the system are, and we are asked to find the transfer function. Okay. Now to solve this, we recall that y of s is equal to h of s times x of s. Now that is true for IC's, the initial conditions, being 0. Okay, if it turns out that you have, which is what we have this time, so we're in good shape, and this is an easier problem to solve here, and that makes us happy here. But in general, if you go back to, and we'll look at this in another video here coming up, if you take the Laplace transform of a differential equation, then whenever you take the Laplace transform of a derivative or power of some ordered derivative, there's an initial condition term. And so in general, once you've cleared things up and you've written, you want to isolate y of s in terms of everything else, you'll find that you have y of s is equal to the numerator over the denominator of the transfer function times x of s, but then additionally you have some initial condition terms divided by the denominator of the transfer function. Okay, so these here are 0 if no ICs, which is exactly our situation here. So that's good. So the approach is that we're going to find h of s by simply taking the ratio of y of s over x of s. Y of s in this case is just the Laplace transform of y of t, and that we've been given. Right? We've been given y of t, so we'll put that in there. And then x of s has been given. It's a unit step, so it's the Laplace transform of the unit step. So we have that. Okay. So we're good to go. Now before we do that, it's good just to take a look at y of t and consider what is this waveform. We have two terms, well, three terms, but the last two are collected together. So the first term is just the ramp. Okay, this is the 3t term. It's just a ramp. And then we're subtracting from that this 1 minus exponential, which will look like this. Alright, so this is equal to something that looks like this. This is the waveform that I brought up in the last video but didn't really go anywhere with it. So now we're looking at what kind of system would be necessary to have that response when a unit step is applied. So maybe you want to pause the video and actually try to work this at this point and then start it up again. The procedure is that you're going to take the Laplace transform of y of t and then the Laplace transform of x of t, the unit step, and then find h of s. Okay, so I'm going to go ahead and solve it now. We have the Laplace transform of the 3 of t, and that's going to be 3. Well, first of all, we have the Laplace transform of the unit step, which will be 1 over s. Right? Now we have the Laplace transform of 3t. Okay, so that's going to be 3 over s squared. We have the Laplace transform of minus 1, and that's going to be 1 over s. We have the Laplace transform of plus e to the minus 2t, and that will be 1 over s plus 2. Right? And now we put this all over a common denominator. So we'll have s times, and then we have, let's say, 3s minus, 3s times s plus 2 minus s times, take that back, the first term was wrong. We have 3 times s plus 2 minus s times s plus 2 plus s squared all over s squared times s plus 2. And if we collect the terms, let's see, we have 3s plus 6 minus s squared minus 2s plus s squared. So the s squareds cancel, and we are left with s plus 6. I hope I'm doing this correctly here. S plus 6 over s times s plus 2. Okay. Let's look at the pole zero plot for this. So the pole zero plot would have a pole, a pole at 0, a 0 at minus 6, and another pole at minus 2. And notice that if we put in an input, that's a step, and you get a response, that's a ramp, even though it's, it's got this exponential offset, or 1 minus exponential offset. The bottom line is, at the end of the day, the output is an integral, or includes an integral of the input, and so there has to be an integrator. And so you'd expect a pole at 0.